Welcome. In this video, we're diving into an incredibly important topic in precalculus, conic sections. You'll be able to represent these fascinating shapes with equations and understand their key features. So, where do these shapes come from? They are literally sections of a cone. Imagine two cones placed tip to tip with a flat plane slicing through them. The shape of the cut that the plane makes is what we call a conic section. If the plane is parallel to the base of the cone, you get a circle. A slightly tilted plane gives us an ellipse. A parabola is formed when the plane is parallel to the cone's side. And finally, if the plane is vertical, it slices through both cones, giving us a hyperbola. In this video, we'll focus on analyzing these shapes through their equations and understanding their key properties. Let's begin with the parabola. You're probably familiar with parabolas from quadratic functions. Our goal here is to be able to write the equation of a parabola when its vertex is not necessarily at the origin. Parabolas have a line of symmetry and a vertex, which is either the highest or lowest point. The vertex is represented by the point, hk. A parabola can open up or down. For these, the equation is y minus k equals a times the quantity x minus h squared. This looks a lot like our standard quadratic form, but shifted. The vertex is at the point hk. A parabola can also open sideways. Its equation is slightly different. For a parabola that opens left or right, the equation is x minus h equals a times the quantity y minus k squared. Notice that x and y have swapped positions compared to the vertical parabola. The vertex is still hk. Now, let's work through an example. Suppose we want to find the equation of a parabola that has a vertex at the point 4 minus 2 and opens to the left. First, we need to choose the correct formula. Since the parabola opens to the left, we use the formula x minus h equals a times y minus k squared. So, we start with the equation x minus h equals a times y minus k squared. Next, we identify the vertex, which is 4 minus 2. This means h is 4 and k is minus 2. We can see that h equals 4 and k equals minus 2. Now, we substitute these values into our equation. Plugging them in, we get x minus 4 equals a times the quantity y minus a negative 2 squared. This simplifies to x minus 4 equals a times y plus 2 squared. Notice that since the parabola opens to the left, the value of a must be negative. The problem didn't give us enough information to find a exactly, but we've successfully set up the general equation for this parabola. So, our final equation is x minus 4 equals a times y plus 2 squared, where a is a negative constant. We have now learned how to write the equation of a parabola from its vertex. Our next conic section is the ellipse. A circle is a special kind of ellipse, so we'll cover both together. In this scene, you will learn to write the equations for both ellipses and circles. An ellipse is like a stretched circle, defined by a center point, hk, a horizontal radius a, and a vertical radius b. This means that the distance from the center to the ellipse along the x-axis is a, and along the y-axis is b. The standard equation for an ellipse centered at hk is the quantity x minus h squared over a squared plus the quantity y minus k squared over b squared equals 1. The key feature here is the plus sign and the equation being equal to 1. Now, let's talk about the special case, the circle. A circle is simply an ellipse where the horizontal radius a is equal to the vertical radius b. Let's call this common radius r. If we substitute r for both a and b in the ellipse equation, we get x minus h squared over r squared plus y minus k squared over r squared equals 1. If we multiply the entire equation by r squared, we arrive at the familiar standard equation for a circle, x minus h squared plus y minus k squared equals r squared. In this equation, hk is the center, and r is the radius. We have now seen that a circle is a special case of an ellipse. Let's work through an example. Find the equation of an ellipse centered at minus 1, 3, with a horizontal radius of 5 and a vertical radius of 2. First, we identify our parameters. The center, hk, is minus 1, 3, so h equals minus 1 and k equals 3. So h is minus 1 and k is 3. The horizontal radius a is 5, and the vertical radius b is 2. And our radii are a equals 5, b equals 2. Now, we plug these into the ellipse formula. x minus h squared over a squared plus y minus k squared over b squared equals 1. Substituting the values gives us x minus a negative 1 squared over 5 squared plus y minus 3 squared over 2 squared equals 1. Simplifying, we get our final equation, the quantity x plus 1 squared over 25 plus the quantity y minus 3 squared over 4 equals 1. This ellipse is centered at minus 1, 3, has a width of 10 and a height of 4. Finally, let's explore the hyperbola. By the end of this scene, you will be able to write the equation of a hyperbola and understand the role of its asymptotes. Hyperbolas look like two parabolas facing away from each other. They are defined by a center h, k, and two fundamental axes. The equations for hyperbolas are very similar to ellipses, but with one key difference, a minus sign. For a hyperbola that opens left and right, the equation is x minus h squared over a squared minus y minus k squared over b squared equals 1. The fact that the x term is first, or positive, tells us it opens horizontally. For a hyperbola that opens up and down, the y term comes first, y minus k squared over b squared minus x minus h squared over a squared equals 1. If the y term is first, the hyperbola opens vertically. Every hyperbola has asymptotes, which are lines that the hyperbola gets closer and closer to but never touches. The equations for these are important. The asymptotes for any hyperbola centered at h, k, are given by the equation y minus k equals plus or minus b over a times x minus h. These are straight lines passing through the center. A great way to visualize this is with the asymptote rectangle. You can draw a box centered at h, k, with sides of length 2a and 2b. The asymptotes pass through the center and the corners of this box. The hyperbola then approaches these lines. Visualizing the asymptote rectangle, formed by drawing lines x equals h plus or minus a and y equals k plus or minus b, helps you sketch the asymptotes. Let's work through a final example. Find the equation of a hyperbola centered at 2, -1 that opens up and down with a horizontal length of 2 and a vertical length of 6. First, the center hk is 2, -1, so h equals 2 and k equals minus 1. Our center is at 2, -1. The horizontal length is 2, which means 2a equals 2, so a equals 1. The vertical length is 6, so 2b equals 6, which means b equals 3. The horizontal radius a is 1, and the vertical radius b is 3. The hyperbola opens up and down, so we use the y first equation, y minus k squared over b squared minus x minus h squared over a squared equals 1. We use the y first formula, since the hyperbola is vertical. Substitute our values. We substitute, getting y minus a -1 squared over 3 squared minus x minus 2 squared over 1 squared equals 1. Simplifying, the equation of our hyperbola is the quantity y plus 1 squared over 9 minus the quantity x minus 2 squared over 1 equals 1. What about its asymptotes? The asymptote equation is y plus 1 equals plus or minus 3 over 1 times x minus 2, which simplifies to y plus 1 equals plus or minus 3 times the quantity x minus 2. These lines guide the shape of the hyperbola. We have now learned how to write the equation of a hyperbola and its asymptotes. Let's quickly recap what we've learned in this video. We started by understanding that conic sections, parabolas, ellipses, circles, and hyperbolas, are all formed by intersecting a plane with a double-napped cone. We saw that each conic section has its own standard equation. The key to mastering these is to recognize their structure and how the components relate to the graph. Remember the key differences. The parabola has only one squared term. The ellipse and circle have two squared terms added together, with the circle being a special case where a equals b. The hyperbola also has two squared terms, but they are subtracted. The constants h and k always represent the horizontal and vertical shift of the center or vertex, and the values of a, b, and r define the shape and size. By identifying hk and ab or r, you can determine the key features of the conic and sketch its graph. Conversely, if you know the key features, you can write its equation. Now you are able to represent conic sections analytically. Thank you for watching.